your final exam right after class today, so you can get started on that. You might or might not need office hours once you see the exam, but you'll just have to see the exam to understand what I'm getting at.
Feels like we will.
But you have until next Thursday at 5:15. That's the end of our exam period, is next Thursday.
Smiley face.
Are there office hours next week?
Say it again?
Are there office hours next week?
Yeah, I can certainly have office hours, but I think once you see the exam, you'll understand what I'm getting at, and you're also welcome to just email me questions, which will probably be sufficient, but I'll be happy to hold office hours if people need them, but when you see the exam, let me know, okay?
One of the questions.
Huh?
I was asking you a silly question, and that was
I was saying a silly thing, so we're both on board with that.
Okay, all right.
So if one of the questions. Go ahead, Sarah.
I was just gonna ask if we can hang out with you at office hours.
Yeah, of course. You can just hang out with me at office hours. Yeah, that's cool. I like it. Okay, I'm going to get started because I do have to talk about some stuff today, believe it or not. And it's really, really interesting. We are going to use the ideas that we've been developing, but we're actually going to take a huge dramatic turn starting today, but really finishing on Thursday. And as I promised, on Thursday, we will get to the point where we realize the need for string theory. But we won't get into string theory, but we'll at least realize the need for it. Okay, so I'm going to start with what I like to call a classical fairy tale. Okay? And don't let the word classical imply the wrong thing to you. This is not like classical because it was written in the 17th century. This is classical because...
It has to do with classical mechanics.
Yeah, it's not quantum. But don't get me wrong, I'm going to do the quantum fairy tale in just a minute. Oh, hold on. I got to grab something. Just a second. I'll be right back. There we go. I have them. We're good to go. Okay, yeah, Madison's a good topper. All right, so here we go. Suppose that sitting out in the universe was some charge, and I'm going to make it a negative charge, so I'll put the little minus up there. But there was just some charge that was sitting there, and we were interested in measuring the size of that charge. Okay, sound pretty reasonable, right? What would you do? Madison.
What? Yeah.
How would you measure the charge?
I would do like the bubble chamber thing or whatever.
Yeah, you can do something like that. So what I had in mind, and this is kind of exactly what you're talking about, I would take a known charge, say an electron, and I would shoot the electron towards this particle, and it turns out that if I know how much energy I'm giving the electron, and I know the impact parameter, okay, so this is not aimed directly at the charged particle, it's actually aimed a little bit above, and the horizontal or the vertical distance is the impact parameter b, then it turns out that, and let me, so I had to rewrite my notes, and I've got to look at the old copy because the new copy I can't really see because it's small. But it turns out that if we do this experiment, then we know what the charge is going to do. It's going to come in and it's going to deflect because the electron has a negative charge, this has a negative charge, so it's a repulsive interaction. And then we can talk about, okay, what is the angle of deflection, theta? And it turns out that in this analysis, there's a really simple formula, and we can solve that formula for the value of the charge of this thing, and that's going to be 2 times the impact parameter times the energy of the electron that's coming in over QE, which is the electron coupling, times cotangent of theta over 2. Okay? Now in this analysis, I'm going to make the assumption that this thing is hella huge. It's so massive, it's way more massive than the electron, so it's actually not going to move when the electron comes upon it. It's going to be kind of like the Earth and a satellite scattering, okay? And that's where this simple formula came from. The formula would be more complicated if the Q prime, or if the Q minus charge actually moved. Okay? So does this experiment make sense? Give me a thumbs up. You know, a lot of you, I can't see your thumbs. I don't know if you're holding your thumb. No, I can see your thumbs, my video friends. But all these other people, I don't know if you're like thumbing your nose. Okay, that's better, that's better. Okay, so again, all we have to measure is the impact parameter B, which is a distance. We know the electron charge, and we set the energy. And then the only unknown is, we measure the scattering angle theta, we put all that in here and we get the Q minus. Okay? Now we're going to make this story a little more interesting. And this is still a classical fairy tale. I'm not going quantum yet. Okay? So now what I want to do is I want to consider taking Q minus and giving it some friends. Seem reasonable? So what I'm going to do is I'm going to put Q minus inside of a dielectric material. That's the technical name of friends. Okay? But what we know, and if you forgot about the notion of dielectric, it's pretty simple to remember, but I don't blame you if you forget things, because I forget a lot. A dielectric material is simply composed of atoms or molecules which have an electric dipole. So there's a separation between the positive and the negative charges. And so what we can imagine is if we put this large negative charge in a dielectric medium, then what's going to happen is all of these polar particles are going to reorient themselves with their positive charge pointing towards the Q minus and their negative charge pointing away. Okay? So you got to give me a couple of minutes because I've got to draw this exactly right. Otherwise, what I'm about to say is going to get screwed up. Okay, so if you can't see this, this is just a line with 2 dots on the end. The positive charge is closer to Q minus, the negative charge is away, because we know that the positive charge is attracted to the Q minus and the negative charge is repelled. And then I'm just going to draw another layer of them. And we'll draw some here as well. Okay, so everybody understand what I'm drawing here? We good? Yeah, I mean, this is a big negative charge, so it's going to attract all the positive ends of things and it's going to repel the negative ends. So everything's going to orient itself so that it looks like this. Okay? Now, well, let me ask you a question. In this story, how much charge does Q minus exhibit when I'm here? I'm pointing there. I'm that far away. How much charge does Q minus exhibit?
Q minus?
Yes, thank you. It exhibits Q minus charge. Okay? What about here?
Not quite Q minus.
Yeah, so here we actually have to draw a Gaussian surface. So maybe I'll draw a Gaussian surface here. And then the charge that is experienced by something at the radius of this circle is the net enclosed charge, okay? So R small is enjoying Q minus, but we've got 4 positive charges in there. So we've got Q minus plus 4E plus, because it's a positive electron charge. However, if we were further away from the center, say we were out at this radius, then we would, in our volume, we would include all of these pairs, but these pairs cancel because they're positive and negative. So we would only include 1, 2, 3, 4, 5, 6, 7, 8. 8 positive charges. So at the larger radius, we would have Q minus plus 8 positive charges. Okay? What do we call this effect? Nico? Yes, you.
Yeah.
Come on, man, I'm giving you a hint.
I have no idea what you're doing. Are you summoning a demon?
No.
He's screening himself.
He's protecting himself.
I'm screening myself.
Shield.
I'm screening myself. This is the screening phenomenon, okay? All it says is that the further away I get from this charge, the smaller its value will be because I'm getting this screening that's enhanced the further away I get. Okay? Does that make sense? So here's the thing. If we did the experiment sending in an electron at some impact parameter B, we're again going to have the electron deflect, and we can talk about the angle of that deflection, but the answer is no longer going to be this simple, right? Because now the charge that the electron is experiencing is position dependent. The closer you are, the more of the fundamental charge you sense, but the further away you are, the less of it you sense. Does this make sense? Okay? So, one of the ways that we can sort of encapsulate this is we can say, well, first of all, let me say this. So if I fix the impact parameter B and I keep that the same, if I increase the energy that the electron gets, it's going to get closer to Q minus. Okay, generally speaking, if I give this thing a hell of a lot of energy, like, super duper amounts of energy, it's just going to go in a straight line right over this. The less energy I give it, the sooner and the more it will deflect. Does this make sense? Okay, so the theta obviously depends on E. It also depends on E in this case. But the more energy we give it, the closer it's going to get to Q minus. The less energy we give it, the further it's going to be from Q minus. And so what we could do is we could say the following. We could say that the effective charge, Q minus, is a function of, and we might as well call it, I'm going to call it the momentum of the electron P. I can interchange the momentum of the electron and the energy of the electron. They're interchangeable. But the effective charge that is measured here depends on the momentum of the electron, because the momentum of the electron is going to dictate how close I can get to Q minus, and that's how much shielding I'm going to be able to see through. Okay? Now, very important observation. Is this Q minus? Are these the same? Hunter, Thompson.
I don't believe
No, that's what I just said. This includes the shielding. This is the fundamental charge of this thing that's sitting here. Okay? So when I do the calculation, the best that I can get at a fixed momentum P is the effective charge. Now, if I knew all of the details of this material, I could probably take this and I could probably relate it back to the fundamental charge. But let's just suppose that this is some dielectric medium whose properties I'm not particularly sure about, okay? Now, there are two ways to get around this. And is Dylan on? Yeah, Dylan, you're on. Dylan.
Yeah.
Can you tell me one method you could use to actually measure the honest value of Q minus instead of this effective charge? There's two methods, give me one.
I don't know, like, you could go really close.
Yeah, if you give yourself a hell of a lot of energy and you get closer to Q minus than the nearest dielectric particles, now you have to have a small enough impact parameter for this as well, but even if you have a super small impact parameter, if you have low energy, you'll deflect. So you need a small impact parameter, you need a hell of a lot of energy, and if you can get close enough to Q minus that there's none of these screening particles in the circle, then you're measuring the actual honest value of Q minus. Keep that in mind, okay? What's another way of determining the actual value of Q minus? And this way is a little more pedestrian. Josh Lewis, has his picture card.
That is me.
Yeah. What's another way to get the honest value of Q minus?
To scoop it up. Look at the board.
Yes, scoop it up and out of. Scoop it up and out of the. Rhymes with dielectric.
Dielectric.
Yes. Yeah, if we just say this dielectric is screwing me up, I'm just going to pull the charge out of the dielectric and do this experiment on it, then I'll get the fundamental amount of charge, right? It seems silly, but it's going to be important in the example to follow. So is everybody on board? Okay, good. All right, so now let us turn to a quantum fairy tale. Okay? So in the quantum version of this fairy tale, we can kind of sketch out what this looks like. We can say, okay, I'm going to have this large Q sitting there. I'm going to have some electron coming in, and that electron is really going to deflect, but the picture is actually going to involve the interaction through the exchange of a photon. Okay? Now that almost looks like a Feynman diagram, but not quite. But we could give it a few legs here, even though the Q minus we're assuming to be at rest. But now this looks more like a Feynman diagram, right? We have an incoming and outgoing, and incoming and outgoing at a virtual exchanged photon. Okay? So now, don't get me wrong, you can calculate the probability that the electron will deflect at an angle theta. And then if you repeat this experiment a gazillion times, then you should, find the percentage of theta scattering angles should agree with what you calculate for the probability. But, and so that's how you actually, do calculations and compare them to data in a quantum system. You can't just do a single, experiment and go, oh, the angle is blank because, quantum mechanics doesn't give you definite results. It's all probabilistic. Okay, but this isn't the end of the story, because remember that in addition to that diagram, we have this one. Right? Where I'm just adding in a loop of virtual particle-antiparticle pair, where can be built based on the QED vertex. So this is a totally allowed diagram. Of course, it's higher order than this one. So you might deem that this plays a smaller role, but nonetheless, it's there. Okay? But wait a second. If this is an electron and this is an anti-electron, one is negatively charged and one is positively charged, what might they do in response to the charge Q minus?
Speed up or slow down?
Speed.
Interact with it?
Well, actually, they could polarize.
Okay.
Okay? Now, don't get me wrong, these are virtual particles. When do they exist? When do they not exist? Do they exist? It's kind of weird, but I'm just giving you a picture here, which we're going to follow through with a calculation. But I just want you to imagine that here you have a positive and a negatively charged particle, so they could polarize themselves and effectively shield the overall charge of Q minus, which is going to change the answer for the scattering of E.
Oh, jeez.
Okay? Now, that's kind of interesting, but tell me, is it possible, like we do here, to grab the Q minus and pull it out of this virtual dielectric? Is that possible? Who says yes? Who says no? You guys are shy. No, you can't get rid of this effect. Like, this is quantum field theory. Like, that's the truth of the universe. This is unavoidable. Here you could just pull the particle out and have it be bare and naked, and you can measure its charge just by running this experiment. But here, there's no sense in which you can just run this experiment. This is always going to be included as our higher order diagrams. Remember, you could put another circle in here and get 2 shielding particles. Okay. Now, we haven't talked about the amount of shielding or anything, but it's definitely a part of this story. Okay? So, what I'm going to do now is I'm going to quantify this. I'm actually going to do some calculations. They're not that bad. But I'm going to actually show you the means under which this is actually impacting things. So let's see. Okay. So for starters, I'm going to imagine that instead of using an unknown charge here, I'm actually going to use a known charge, and I'm just going to pretend I don't know its charge. So I can talk about how would I use the information here to determine the charge of this thing, where this thing I'm going to use is a muon. Just because a muon, we know its particle properties. We know it's a spinner, so if we're doing Feynman diagrams, we've got to put in spinner factors. I could just say this is a spinner, but if I'm not telling you even what Q is, you might be like, there's a collection of spinners. Oh my God, I don't know what the hell that is. Okay, so we're going to do just an electron and a muon, scattering, of course, into an electron and a muon. All right, and of course, we have the approximation that the muon is way, way bigger than the electron, so we can largely assume that the muon doesn't move, so that's fine. And now let's draw the first order diagram. And you should all be able to draw this without watching me draw it, because by now you should know how to do this. Okay? I'm going to go ahead and label the momenta. Okay? So there we have the lowest order contribution to this process, or the matrix amplitude of this process, M. Okay? And it turns out that the M that is associated with this, which I'm going to call the tree level M, this is the tree level because it doesn't have any loops, because trees don't have holes in them. Well, some of them do, but most of them don't. So we call the diagrams without any loops in them the tree level. So the tree level amplitude for M, you guys should know how to do this, because all we do is we follow the particles in, we write down a spin factor for that, then we have our vertex, we follow the particle out, so we get a spinner sandwich here with a vertex factor. We do the same thing here, and then we throw in an internal propagator for that photon. This is pretty simple. Okay, so at the end of the day, this is going to give us minus GE squared. Let me move this over a little bit. And then we're going to have a spinner sandwich, which is composed of U bar 3, gamma mu, U1. So that's this guy right here. And then eta mu nu over Q squared, U bar 4, gamma nu, U2. Okay? Where that is not supposed to be Q, that's supposed to be Q squared. It's not supposed to be Q2, it's supposed to be Q squared. Okay, now, granted, you know, when I wrote this down, I would have been writing down delta functions, conserving the momentum at each vertex, and then I would have had to have integrated over this internal Q. But this diagram is so simple that it turns out you can do all of the integrals with the delta functions, okay? So this is the post-integration phase of this amplitude. And the Q here is just the momentum transfer. So the Q we can write as P2 minus P4. So we can write this totally in terms of the external momenta, but calling it Q is going to be useful later on. It's basically the momentum that is exchanged. So you can imagine that P2 changes by an amount Q, giving me P4. Okay? All right. Okay, so now, is this the end of the story? Okay, I'm going to do something here. I'm going to open up the chat room. I don't want to see what's in here. Oh my God. Oh dear God. Okay, I'm going to close the chat room and I'll read all your chats later. Okay, Sarah, what is the next order diagram going to look like?
I'm sorry, I had to find the unmute button.
Yeah.
It's gonna have either a circle in the middle, or you can connect the bottom or the top, I think, right?
Yes. There's actually quite a lot of diagrams at the next order. Okay, it's a fourth order thing. It's going to turn out, for reasons which I'll talk about next time, that there's only one diagram that really matters for what we're going to talk about. There are many diagrams, but I'm only going to have to focus on one, and I'll share with you why in our next lecture. But the diagram that matters is probably the diagram you would expect based on what I drew earlier, but it looks like this. I know, it's funny, isn't it?
Yeah.
Yeah. Okay, so I'm going to go ahead and label this one up. And I'm going to keep the same external labels. Okay, this is going to be Q. Now, I'm going to be a little quick on this, because this is something that we've done enough. In principle, I should label this with an internal momentum, this half with an internal momentum, this half with an internal momentum, and this with a different momentum. All four of those momenta should be different, okay? But when I also write this down, I have to put a delta function conserving momentum here, 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 and here, and then I have to integrate over all four of these momenta. Well, you can imagine when you use the delta functions to evaluate the momenta, you'll find some things which were a priori pretty obvious. For example, whatever momentum is carried right here, you have to have the same damn thing carried here, because whatever momentum is released from this interaction, it's bubbleitized, but then it's just condensed back to a single photon. So the conservation of momentum says this momentum has to be equal to this one, which again would follow if you put in the delta functions and then you integrate it over all the different momenta, okay? Moreover, if I say that this particle is moving with a momentum k, then I could immediately say that this particle must be moving with a momentum k minus q, okay? So basically, all I'm doing is I'm saying, okay, there's a free momentum parameter in here, but the total upwards momentum carried in the circle still has to be q, because momentum has to be conserved. So I have q here, I have q in the circle, and I have q up here. Now, people get confused. Why is this k minus q and why is this k? Well, this is k minus q because it's going down. So if I sum the momentum at this vertex, I would have q coming in, I would have k going out, and then I would have k minus q coming in, which is what I expect for conservation of momentum at that vertex. Okay? So at any rate, what does this give me for the one loop contribution? Well, the nicest part of this is that I have to create spinner sandwiches with these external lines in this vertex, these external lines in this vertex, but those look the same as those. Okay? I'm also going to have internal propagators associated with these two pieces of the photon, so I'll have two internal propagator factors, but then I have to treat this thing, this internal loop. And I actually explained how to handle an internal loop at the end of our QED practice lecture, which you might not remember, but it's fine. All we do is we take this internal loop and we say, okay, there's a propagator here, there's a vertex here, there's a propagator here, and then there's a vertex here. So all I have to do is, in a cyclic order, and it doesn't matter where you start, I need to write down the propagator, the vertex, the propagator, the vertex. And I can start on the vertex, propagator, vertex, propagator. It doesn't matter, because at the end I'm going to take the trace. And the one thing you know about the trace is that you can cyclically permute it, which means you can start anywhere. Okay? So the contribution from here is going to be a trace over two vertex operators and two propagators. All right, so I'm just going to write this thing down. It's not going to be as bad as you might think. Yeah, it's going to be pretty hella bad. So, let's see. One loop. Here we go. And this is what I need these for. Oh. So Avery, if you have a joke, now's the time to tell it. It's going to take me a minute to write this down.
Can we talk more about Ents from Lord of the Rings?
Say it again?
Ents from Lord of the Rings.
Sure, yes, go for it.
You're gonna love the chat, man. It's pretty good.
It is pristine today. What do you think? What do you think of Ents?
I don't really have any opinions on ends.
Yeah. What? Share an opinion. Give us a controversial opinion.
Ends think campfires are racist.
Yeah.
Yeah.
I think they're right.
Mm-hmm. Shut the fuck up, Avery.
What? Incorrect, Avery.
Oh, I have a joke. It's all right. Quitting before you're fired, right before you're fired, is like aborting a miscarriage.
Is this the part where I drink?
This is where you eat the miscarriage.
Yes, this is the part where you drink. Here we go. All right.
If I could drink, I think I'd need a lot to get over this.
Yeah. Getting over Avery requires a lot of alcohol.
Boof it, Ross. Boof it.
Getting over it.
Okay. That's enough. Thank you for your entertainment. Why is it every time I tell Avery to tell a joke, he doesn't? It doesn't matter. Okay, so, shut up!
I tried to, but it wasn't funny.
Okay, that's fine.
Oh shit, you're...
Okay, so here are the spinner sandwiches. They're the same as up here. Spinner sandwiches, same as up here. The GE squared comes from the two vertex factors here and here. Similarly, there's a GE squared that comes from this vertex factor and this vertex factor that's the middle of these spinner sandwiches. But now we have this thing, which is going to include Yeah, so this is going to include our treatment of the virtual particles. So we've got the trace of gamma mu over gamma mu over I don't have these organized in a way which I can point to them and say that's the propagator, that's the vertex operator, but all the information is there, so we won't worry about trying to trace through it. Here is the important part of this story. These things are going to give me numbers, right? This is just a spinner sandwich, and at the end of the day, it'll give me a number, or it might be a function, but it's just going to be something that I can evaluate. So to this has an undone integral, k. Now look at what k is. K is how much momentum this virtual particle is carrying. Of course, this virtual particle must be carrying k minus q, where q is this momentum, and that momentum q is going to be again determined by p2 minus p4. But k is literally a variable which can take a range of values, so we have to integrate over the possible values of k. Okay? K is not fixed by the dynamics of the problem in the way that q is fixed by the external momentum of the problem. That's a very important observation. So what I would like to ask is, here's the integral over k. What do you think it's going to be? Well, let's just do a counting of the powers of k. So d4k can actually be broken down into k cubed times dk, including differentials of angular parts. Okay, so remember, if you're in 2D and you have, if you're in 2D and you have a circle and you want to integrate over the polar coordinates, then you just have a factor of r dr. If you're in 3D, you get a factor of r squared dr plus d theta d phi, or d theta here. In 3D, you just get a factor of, or sorry, in 4D, you get a factor of r cubed dr. Okay, does this make sense? I mean, you know, the dimensions of r cubed and dr is 4, and that's giving us our 4 spatial dimensions. So this d4k is going to give us a contribution of k cubed dk. There's a k there, and there's a k there. This is k slash, so that's gamma mu k mu. This is gamma mu k mu, and this is q slash, so it's gamma mu q mu. But this has basically got 2 more powers of k in the numerator. And then across the bottom, we've got k squared, so we've got k to the 4th in the denominator. And so this is going to give us an integral of dk, which is an integral of k. Okay? What are the limits on this bad boy? What values can we allow for that internal momenta k? What is all of them?
Every single one.
Yes, thank you. That means 0 to infinity. Okay? Is that bad?
Yep.
How much is it?
Little.
How much is it?
It's infinity.
It's infinity. Thank you. Thank you so much, Ross. I really do appreciate it. So, well, let's think about it. This contribution to the amplitude m is going to be finite. There's no integral there. It's just involving fixed values of things. I mean, remember, q here is just the difference in these external momenta, which you can measure or set or whatever. So this is definitely not infinite. But this contribution is getting all the same stuff here and here, but it's getting this infinity factor in the middle. Okay, how many of you have heard of an infinity in quantum field theory? They're everywhere. Everywhere. And so what we're going to learn about today and next time is how to deal with those infinities. We're going to get started today and then we'll finish up the story next time. Now it turns out that this is a naive counting, and this thing actually has some delicate cancellations that happen. So in truth, it doesn't diverge like that, rather it diverges as the logarithm of k. But still, going over the range from 0 to infinity, even the log of k is going to give us an infinite response. Okay? So, how are we going to handle this? Well, let's do the following. I want to take this guy right here. So it's just the integral term. The IGE squared is just going to come along for the ride. I want to call this minus I eta mu nu times a function of q squared. Okay? Now, after we do the integral, the k is gone. Okay? So really the only thing that this is going to hang on to in terms of dependence is q, because q, you can vary. All right? The eta mu nu, we'll notice this has got the trace of gamma mu, gamma nu, and you might or might not remember, but the trace of gamma mu, gamma nu is 4 eta mu nu. So that's where this eta mu nu thing is going to pop out of this. You can't necessarily see it immediately because you can't take the gamma mu and the gamma nu and put them right next to each other. But these two indices have to come out of this integral expression in the form of something, and the only thing they can come out in the form of is the metric. Because the gamma factors, they're just constant matrices, and so they need to give rise to another constant matrix, which is, of course, the metric. Okay, so this IQ squared, this integral, can actually be recast, and trust me, there is a shit ton of work that goes from here to what I'm about to write. So you'll just have to accept what I'm about to write, but then we're going to take that, we're going to go quite a ways with it. So this is what IQ squared looks like. Oh boy, oh boy, oh boy. So let me see. Okay, so IQ squared takes the following form. Minus 1 over 12 pi squared times the integral from m squared to infinity. Oh, sorry. Sorry, I should have told you what these masses are. These are the mass of the electrons because remember, I'm doing a pair of virtual electrons here. Okay, so this is going to be the mass of the electron is the lower limit of this. Okay, yeah. So this is going to be the integral from the mass of the electron squared to infinity of dz over z minus, and this is going to be ugly. I'll come over here. Minus 6 from the integral 0 to 1, z 1 minus z, natural log 1 minus q squared over me squared c squared z1 minus z dz. And there's one more bracket. I have to put that. Okay. Holy cow. So again, this is minus 1 over 12 pi squared times this whole thing in parentheses, and this is integral from the mass of the electron squared to infinity of dz over z. So this is obviously a dimensionless integral. Minus 6 times the integral from 0 to 1 of z times 1 minus z times the natural log of 1 minus q squared over m squared c squared times z 1 minus z dz. Okay? This is not inspiring, it's not beautiful, it's ugly as shit, but there's an important takeaway from this. Okay? What do you think you get when you integrate dz over z from me squared to infinity? Ross.
Oh, I'm sorry, I didn't quite catch that. What was it? Okay, so when you take dz over z from 0 to infinity, you get infinity.
Yeah, you do, because this is just going to give you a logarithm of z, and that's going to give you infinity. Okay? So this is going to give us infinity. What's that going to give us?
That will also give us infinity.
It will?
Well, because there's a z times z plus 1, like natural log there, so it's like a polynomial times a natural logarithm.
And? Why is it going to give you infinity?
Well, because it diverges, because the function itself will go to infinity at infinity, and therefore its integral will as well.
Is the integral going to infinity?
So it's going from 0 to
1.
0 to 1. Oh, I'm sorry, I couldn't see the 1 there. Okay.
That's okay. That's okay. That's why I read it out to you. Yeah, this guy is only being integrated from 0 to 1. Okay?
Okay.
So this thing, I mean, you know, squint your eyes. You probably can't even read the damn thing. That's why I read it out to you. But if you squint your eyes, you can argue that this is finite. And it is. Okay? Now, what I'm going to do is I'm going to introduce a function here. Oh my gosh, I'm squatting down. I can't believe it. Which is basically a function of minus q squared, because in all of this, the z is integrated over, so the only thing that is variable in here is q squared. So I'll call this a function of minus q squared. And the reason I'm going to do that is because q squared is actually less than 0. This is almost the mass shell condition. Well, actually, it is the mass shell condition, okay, where I take a 4 momentum and I square it, and I ended up getting minus m squared c squared in this new convention where we changed the signature of the metric. So I'm just calling minus q squared a positive number, okay, because q squared itself is negative. And all you need to know about this function minus q squared is that at q squared equals 0, this function vanishes, okay? And it gets larger the larger q squared gets, okay? That's all you need to know about that function. Okay. So, what I have accomplished by taking this integral and writing it in this crazy-ass form is that this was infinite, and this, too, is infinite. Isn't that awesome? Infinity equals infinity. Fuck yeah. Yeah, no, okay. So now is where we can make a very important observation. First of all, we've isolated infinity. And now what I am going to do is step 1 of what is called the renormalization program. Step 1 of the renormalization program is to take your infinity and somehow, through any means necessary, remove it. So the way that I am going to remove the infinity is I am going to replace the upper limit on this integral with a finite value, which I'm going to call MC. That's not MC squared, but M lower c, because the C here stands for cutoff. Okay? So I'm going to integrate this integrand from ME squared to MC squared. And if MC squared is finite, then this integral is obviously finite. All right? So if I introduce this cutoff, and there's many different ways to finitize an amplitude. For example, one of my favorites is called dimensional regularization. That's where you take the entire thing and instead of formulating it in 4 dimensions, you formulate it in 4 plus epsilon dimensions. And when you're not in 4 dimensions, things become finite. And then if you take epsilon to 0, things go back to being infinite. Okay? There's also polyvalars. There's various ways of doing this. This is just introducing a cutoff to the integral whose upper limit was originally infinity. We're just going to set a finite number there. Okay? All right, so of course this integral is pretty simple. It's just going to end up being a logarithm of the argument, and then we put in the limits and we combine them into a fraction as opposed to a difference. And so what I can now say is that IQ squared is going to be minus 1 over 12 pi squared times the natural log of m cutoff squared over me squared minus the f of minus q squared. So this is going to be my working functional form for this guy right here. All right? I'm going to erase a lot of this. And finally, write down the contributions of M tree plus M loop. All right, now first of all, they both have the spinner sandwiches and the leading minus GE squared factor. And now what we can say is Okay. Looks pretty good. We've got this overall spinner sandwich tracking in this line with that vertex. We've got this spinner sandwich tracking in this line with that vertex. And then what we find is that in this case, we just have the a to mu nu over q squared. So that's the 1. In this case, we get all this junk from the bubble. So we got to introduce this term. Okay? Okay, so now I want everybody to take a deep breath. And get ready, because it's about to become interpretive. And I don't mean the interpretive dance of Nick during our Monodrofold's song at the summer school. I actually mean it's going to become interpretive. All right, so the process that we're studying is this one. And really and truthfully, if you haven't followed what I've done, all you need to do is absorb this. This is simple. This is simple. The 1 is simple. And then this is just the fucked up factor we get from an internal loop. Okay? So the process that we're studying is this one. Where we realize and I know I'm leaving out other 4th order diagrams, okay, but they're not going to play a role in this, which I'll explain to you next time. What do we measure when we send an electron in to scatter off of a muon? Do we measure this, or this, or this, or one of the higher order diagrams? What do we measure?
Yes. Yes.
Do we
Good.
measure all of
I
them
agree with
put
yes.
together?
Say it again, Ross.
Do we measure all of them put together?
Yes, exactly. We measure this. We don't actually measure what's happening internally. All we're doing is we're setting the initial momenta coming in, and we're measuring the momenta that are coming out. That is it for our measurement. So the results of our measurement is the sum of all of the diagrams. Okay? Now, we can do something very interesting though. We can replace all of this by a classical calculation which only involves one diagram. Now I call this classical. It's clearly not classical, it's a Feynman diagram, for God's sakes. Okay? It's a quantum mechanical calculation, but it doesn't involve any of the higher order diagrams. Okay? And what it turns out we can do is, instead of working here, where we're working in terms of the, well, actually the muon charge, here we can work in terms of the effective charge. So let me show you what I mean by that. First of all, look at this expression. And now I want you to consider, instead of working in terms of GE, which is the fundamental electric charge, which is the same charge as the muon, I'm instead going to work in terms of this guy. Okay? Now I want you to take this expression, this is just this definition of this term in terms of this stuff. I want you to take it and I want you to put it in here. What does this become? This becomes M tree plus M loop is equal to minus G U bar 3 gamma mu U1 eta mu nu over Q squared U bar 4 gamma nu U2, where this is the renormalized coupling. Literally, all I did was I took this thing right here and I substituted it in for GE squared times this factor here. You can see that that would happen. But this is the amplitude for that diagram. This is just the tree level amplitude. Okay? So what we've discovered is that by allowing ourselves to redefine the coupling in this way, we can effectively reduce all of these diagrams down to a single tree level diagram. Okay? This is an example of what we call an effective theory. Yeah, thanks Avery. Hope it all goes well. Okay, this is what we call an effective theory. Okay? We can take all of this information and we can replace it by a much, much more simple effective theory where we just have to evaluate this one diagram in order to get the answer. Okay? Now don't get me wrong, these two terms just come from this one and this one. Then you have this one and this. So actually there's a whole myriad of things that go under here. Okay? But of course, the higher order diagrams are going to count less, so we can do the approximation that we're just going to use the lowest two in our discussion. But there'll always be corrections to this. Okay? But at any rate, this is the notion of an effective theory. Now, what's important, what's critically important is that the coupling, and remember the coupling is associated with the charge. So the coupling in this case is a function of the momentum, it's not a constant. It became a function of momentum because of this factor. Okay, that's from the higher order diagram, and that's due to the screening. Okay? If we just had the tree level diagram that contributed, then the coupling would have been constant. But these bubble diagrams are contributing factors which are introducing momentum dependence, and so this thing is going to depend on the momentum. Okay. Let me see what I want to say next. Yes, okay, all right, so let me give you another expression that is useful, and that is the value of this coupling when the momentum exchanged by the two particle is 0, and of course you can do that quickly. Because remember, I told you if q squared is 0, then f of q squared is 0. So this function just goes away when you have gr0. And it turns out that now what we can do is we can rewrite the gr which depends on q squared in terms of this gr0. And so this is going to become gr0 times the integral of 1 plus gr of 0 squared over 12 pi squared times the function of minus q squared. Okay? We good? So, what the hell is gr0? What is gr of 0?
Is that the whatever E number we get in our textbooks?
Exactly. Well, first of all, this gr of 0, sorry, this guy right here, is basically scattering with very little energy. Okay? Alternatively, you can talk about the distance of approach, because the distance of approach and the energy that you give the particle that you're shooting in are inversely proportional. So the smaller the energy, the larger the separation distance. So we can think of low energies as large distances, high energies as small distances. So sorry, Gabriel just said something that was so smart he kind of screwed up my streamline of presenting this, so I got to rethink how I'm going to say it. But I have 3 expressions for the electric coupling. I have gr of 0, I have gr at q squared, and then I have ge. Okay, that was the one that's fundamental. Of the 3 of these, when I go and I look up, the electron charge or the electron field coupling in a book, I see one value. It's just a number, it's a constant. But is it this, this, or this? Well, Gabriel just pointed out that the number that you see in a book is actually this. Okay? Which is, of course, ge square root of 1 minus this plus all of the other corrections. Okay? So this is a quantity that we can actually measure. This is a quantity which we do not know. This is the fundamental electron coupling. It's basically the electron charge. And what I'm telling you is, what we've measured and what is put in books is the effective electron charge with lots of screening. Okay? Let's argue that there's screening when you're at lower energies. Okay? So gr, when q squared is not equal to 0, well, it's gr of 0, 1 plus this thing times f of minus q squared, but what did I tell you that f of minus q squared does if you make q large? It gets big, exactly. So this is taking gr of 0 and making it larger. So this is larger than gr of 0. So what that's telling me is, if I do the experiment at really low energies, I see a gr of 0. If I do the experiment at higher energies, I see a larger value of the coupling, which means that I'm breaking through shielding. So this is just telling me that the charge here is being shielded by these electron-positron pairs. You see less of the charge the further away you are. The closer you get to the charge you're trying to probe, by making Q bigger and bigger, because Q is inversely proportional to the distance, The closer you get, the larger the charge, more of the shielding you're cutting through. Okay, so that's interesting. But now here is the punchline to all of this. There's a cutoff in here, right? There's that MC. What is the actual value of MC? What should it be?
Infinity?
It should be infinity. This MC should be infinity. Remember, we just took the infinity, we pulled it off the upper limit of integration, and we put in MC squared instead. That was our regularization move. We regularized the integral, we made it finite. But that's not the right answer. The right answer is you got to let MC squared go back to infinity. Okay? In which case, this natural log is going to become infinity. Now please pay attention to what I'm about to say. Does that mean that this expression becomes infinite? This is by far the deepest and most important step in everything we're doing today, so please wake up and get this. If this goes to infinity, does it mean that this entire expression goes to infinity?
I don't think so.
Doesn't it become irrational before then?
So I heard Avery say, I don't think so, and I heard Hunter say, doesn't it become irrational?
Doesn't it go to negative infinity?
Well, still, I mean, a divergence is a divergence.
Don't we also have a bunch more terms though, technically?
Sure, but I don't think they're going to save you. So let me ask you this. Is this going to be infinity? Yes, it is, because, you know, everything in... Oh, sorry, I meant to cover that up too. If I cover up the GE squareds, all the other numbers left are going to go to infinity. Here's the thing, and this is the thing you have to process. This entire expression cannot go to infinity because it's the goddamn measured value of the coupling, which is a finite number. This is a number. You can go look it up in a frickin' book. So even though the truth is taking MC to infinity, this cannot be infinite. And there's only one way to dodge that. That is to say that the fundamental value of the electron coupling GE takes whatever form it needs to soak up that infinity. Now let me ask you a question. Maybe, just maybe, this fundamental electric coupling is itself infinite. Maybe it is. Do we have any way to measure that, to figure that out? Do we have any means of measuring the bare electron coupling? That is the electron coupling with no shielding around it, period.
No.
We don't. Remember, when I took the particle in the dielectric, I said all you got to do is send your particle in with enough energy that it gets closer than the nearest atoms that are the dielectrics, that you get closer than those, and then you see the fundamental value. Or you pull it out of the dielectric. You cannot pull an electron out of the quantum dielectric. The quantum dielectric exists, like there's nowhere you can evade it. Moreover, the quantum dielectric is playing a role no matter how close you get. So this fundamental or bare coupling is a physical unknown. We cannot measure it. What we can measure is this, and we got a finite value. So if this calculation seems to be going to infinity because the cutoff goes to infinity, which we know it must, then the only way to explain is that the fundamental value of GE is taking whatever it needs to in order to cancel the infinity. Okay? So, this is what we call a renormalizable theory. That is, we regularized it, but then at the end of the day, after reorganizing things, if we restore the infinity, there has to be at least one parameter that can be adjusted, and this is an unknown bare parameter, whose value can adjust itself to cancel off that infinity. If that happens, then we call the theory renormalizable. You might imagine, though, that a theory could have several different infinities, and then it might turn out that you have 5 infinities, but you only have 4 parameters that can adjust themselves, and so there's no way you can cancel all 5 infinities. In that case, you have what's called a non-renormalizable theory. And we'll talk about non-renormalizable theories next time. Now, this entire story has been a story of basically the electric charge. That's the key ingredient in these electric couplings. So what this is saying is that the fundamental bare electric charge is unknown. The electric charge at zero momentum transfer is what we measure. But it should diverge, so this fundamental electric charge has got to adjust itself in order to make this finite. The same happens with the masses of particles. The mass of the electron diverges. If you set up a problem and you treat the mass of the electron as an unknown, then the mass of the electron diverges, but you don't know the bare mass of the electron. So you let the mass of the electron adjust itself to cancel the divergence. Okay? Now, what I'm getting at here, and I'm going to say this one more time, and then I'm going to finish with one more comment, and then we'll come back and we're going to put all of this story into an understandable perspective, because this first step is huge enough. What I'm trying to argue is, you have a theory which is exhibiting these infinities, and these infinities seem fucked up because if the answer to this is infinite and this is not, then the higher order diagrams are going to be worse and worse and worse. What you're doing is you're saying, no, hold on. The answers are finite. They're parameters I can go measure. The reason I'm getting infinities is because I'm using things which I don't know. Like if I use the measured value of the electron coupling for GE in this expression, then this is a finite number, this is a finite number, this is going to go to infinity. But I'm expressing, no, wait, I don't actually know this quantity. I know this quantity. Okay? The other thing which is important here is that if you're not doing the experiment at zero coupling, at zero momentum transfer, if you're actually sending in an electron with a good amount of momentum, then you need to use this expression. Okay? Because if you use this expression, then you can treat the process by this diagram with Q. Okay? If you use this expression for the GRQ squared, then you have to use this diagram plus all of the loop corrections. This is much easier to use. Notice this expression is in terms of the fundamental bare electron coupling. This one is in terms of the zero momentum transfer coupling. Okay? But most importantly, if you're doing a calculation and you use this form of the coupling, then you just get to use the tree level diagram, whereas if you do this one, you have to use the full set of diagrams. Okay? But what's important about this is the idea that the electric charge that is important for a process is not a constant at all. This is a constant value because it's at zero momentum transfer. But when we do experiments, there's always some momentum transfer. So what you need to be using is the value of the coupling as a function of Q. And this is called a running coupling. Running meaning that it changes its values as we shift the value of Q. That's the momentum that is being transferred in the experiment. So higher energy experiments are going to use the GR with a larger Q squared. Low energy experiments, this is the lowest, are going to use GR with a lower value. Okay? Does that kind of make sense? Masses are too. Masses are not constant. They depend on the momentum of the things which are interacting. This is so far removed from what you're used to because you're used to the idea, oh, I'm going to take an electron and a muon and I'm going to collide them and then I want to calculate what comes out. And I'm going to assume the charge of the electron is fixed, the mass of the electron is fixed, the charge of the muon is fixed, the mass of the muon is fixed. What values are they fixed at? Are they fixed at this? Well, if you're doing the experiment at non-zero momentum, you can't use that. You've got to use this. Are they fixed at this? Well, they are, but I have no idea what the hell that value is. Okay? So we've basically encountered the idea of running of couplings. Let me see if there's anything else I need to say. Yes. Okay. So that's it for today. But I want to just give you a preview of what we're going to talk about next time. This was a technical calculation, okay, and there's more dimensions to this which I'll talk about next time, and we'll actually apply it to QCD because it gives an interesting prediction for QCD, which is relevant for what we've been doing. But it wasn't, and by the way, these calculations were entered into the scientific, know-how in about mid-19th or mid-20th century. But in all honesty, these calculations were given, they made this argument about, oh, the bare coupling, we don't know what it is, maybe it just takes a value, blah, 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 that's infinite or whatever. It was in the 1970s that a guy named Kenneth Wilson actually gave an interpretation to what the hell is going on. And I'm going to share that with you next time, but what's cool about it is that Wilson's interpretation of renormalization goes way beyond quantum field theory, which is largely the subject that we're working with. Wilson's interpretation of renormalization actually shows us how theories are connected as you change the momentum scale at which you're probing. And this is something which should be kind of familiar to you, right? I mean, if I want to describe me, the dynamics of me punching myself in the face, I could start with the quantum mechanics of the atoms in my hands and my face and the air between them and all that shit. But really and truthfully, I don't need to. There's a much simpler description. Believe it or not, going from the atomic description to this very macroscopic physical description involves renormalization. Okay? It's also important if you consider, for example, taking an atomic solid with a lot of little atoms or molecules or whatever, and transitioning from, I know that these are atoms and molecules in this arrangement, and they're shaking and vibrating or whatever, and stepping back from it and going, screw that, I'm just going to think of it as a surface or a smooth manifold. Okay? Again, this is encoding the idea of renormalization. which we're going to talk about next time. Okay? All right, that's it for today. Good night, everybody. And we'll send you a reminder, but 4:30 on Thursday. Don't be late, because we got to end on time to go to the Physics Fest, which I hope you're all going to. Bye.
Dr. Florida,
Yes.
I'm just super curious what my grade is right now. Because we have like 10 and a half hours to choose pass, no pass, if we want to do it.
So if anybody wants to know your grade, just shoot me an email and I'll send you your grade tonight.
Okay, sounds good. Thank you. 10 and a half hours? It's tomorrow at 5 p.m.
Somebody has to do one more chat message. There's 99, and I don't know if it counts up to 100.
It's 20 something hours, not 8, 10 and a half.
Okay, it's tomorrow.
Yeah, I'm sorry I can't do simple addition. That's my bad.
Okay.
I can't either. That's why I didn't specify.
Addition is hard, okay?
Are you getting all
So
what?
what's good about me emailing you your grade is that I'm also going to email you the final, which you can look at and get an idea of how hard it's going to be, and then you can take that into account with your current status and figure out what you should do. Okay, but I've got to go away for about an hour, and then when I get back, I'll start responding to emails with grades, and I'll post the final and everything, but I got to go somewhere for an hour. Are there any other questions? Are you guys just hanging out staring?
No, we good.
You good? All
I
right.
have nothing better to do.
Yeah. Okay. All right. And Ross, I will talk to you a little bit later. Okay. You say it again.
That works.
Okay. All right. Bye, guys.
Bye.
And ladies.